This is the APC 7-1 lecture. We're looking at kinetic energy in this section here. Kinetic energy has the equation 1/2 mv squared. For example, a 3 kilogram duck flying past us at 2 meters per second has a kinetic energy of 1/2 mv squared, which comes out to be 6 kilograms meters squared per second squared, which actually is measured in joules. We associate that number with the duck's motion. That's how much energy the duck has, and it has 6 joules of energy. Since 1 joule equals 1 kilogram meter squared per second squared. The next thing we're going to look at is called work. Work is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. Now, work and kinetic energy have a relationship. We're going to find the expression for that relationship by starting off with F equals ma. We then look at the kinematics equation, G squared equals BO squared plus 2AD. We solve this for A and then plug it up into F equals ma. And we end up with 1/2 mv squared minus 1/2 mv squared equals force times distance. And then what this says is work causes a change in kinetic energy. You have final kinetic energy minus initial kinetic energy equals work. So work equals force times distance. What this also says is that a change in kinetic energy is caused by work caused by a force acting for a certain distance. So to calculate the work a force does on an object as the object moves through some displacement, we use only the force component along the object's displacement. So we have to find the components of that force along in the same direction as the displacement. The force component perpendicular to the displacement does 0 amount of work. So in this case, it would be F cosine phi is the component, the x component that does work in the direction of the displacement. So in this case, it's Ft cosine phi. This is work done by a constant force. And you'll notice in the picture that the initial velocity is smaller than the final velocity. So this thing is increased in speed. And you'll also notice that the kinetic energy bar graph there shows that the kinetic energy has increased also. So this is, you'll see it sometimes F dot D, because that dot right there, that stands for the cosine of phi. It's important to realize, because of what we just talked about, that a force does positive work when it has a vector component in the same direction as the displacement, and it does negative work when it has a vector component in the opposite direction. And then it does 0 work when it has no such vector component. So if the component is perpendicular to the displacement, no work is done. The work kinetic energy theorem is this right here. Change in kinetic energy, which is kinetic energy final minus kinetic energy initial, equals the work accomplished on the object. If we were to look at the work done by a gravitational force, which is a new section here, we'd say work done by gravity equals mass times gravity times displacement times cosine phi. The mass times gravity is the force of gravity. So our work equation stays the same as work equals force times distance, cosine phi. But now we're just looking at the work done by a gravitational force. So here's an example of an elevator here. An elevator cab of mass 500 kilograms is descending with an initial speed of 4 meters per second when its supporting cable begins to slip, allowing it to fall with a constant acceleration. And so look at here's the elevator, our acceleration's in the downwards direction, the displacement's in the downwards direction. And if you look at the forces, tension is up and the force of gravity is down. And you'll notice that since the displacement is down, if we were to look at the work done by the tension, that would be negative work because the force of tension and the displacement are in opposite directions. If we were to look at the work done by the force of gravity, that would be positive because the force of gravity is in the downwards direction, displacement's in the downwards direction, so in the same direction. That is it's positive work. So here we have a question asking, during the fall, through a distance of 12 meters, what is the work done on the cab by the gravitational force? We know it's going to be positive. We know we're going to look at work equals force times distance. So we also want to look at what is the work during the 12-meter fall, what is the work done by the tension, by the upward pull of the elevator cable. And also we want to look at what is the net work done on the cab during the fall. And we also want to see what is the cab's kinetic energy at the end of the 12-meter fall. For each of these, we would simply do force times distance. And we would have to figure these out. So I'd like you to try that out. And this question is actually in the textbook, and you can check your answers and if it's correct. Okay, so pause the video and try this particular problem here. See if you can answer it. And I'm going to put up the answer here in a moment. So here's your answer to part A, 59 kilojoules, and that's how we solve this problem. We'll go ahead and go on to B now. During the 12-meter fall, what is the work done by the cable, or done by the cab, by the upwards pull of the elevator cable? In other words, what's the work done by the tension force? So pause the video and solve this now, please. So we have this solution here. We end up with negative 47 kilojoules. And if you follow this process through, you too hopefully will end up with negative 47 kilojoules. And pause the video and you can work your way through it. The next problem is C. What is the net work done on the cab during the fall? And the net work is just the work done by the tension, the work done by the force of gravity, add those together, and you'll get the net work. So pause the video and come up with that answer now. So our answer comes out to be 12 kilojoules, approximately. And then our last part of the question is question G. What is the cab's kinetic energy at the end of the 12-meter fall? So pause the video and come up with that answer, please. So in this case here, we use the kinetic energy theorem, which says that kinetic energy final minus kinetic energy initial equals work done. And you add the kinetic energy initial over to the other side, you end up with kinetic energy final equals kinetic energy initial plus work. So you go ahead and solve that, and you end up with 16 kilojoules total. This is the end of this lecture. We should have learned about kinetic energy work and the kinetic energy work theorem and how they go together.